Good morning. Welcome to episode 6 of AI engineering. Today I'm going to be going over what we left off with in day 5. This label our receiver and cornerbacks and give it all to the AI. So it's been a while since we looked at this, the holiday, Thanksgiving, all that fun stuff going on. So let's try to pick up right where we left off and keep it moving. So we remember that we were deciding between if we would work with apples and oranges or just go ahead and start working on actually determining the difference between receivers and cornerbacks. We decided to go with the latter, um, which leads us to now being here where, let me pull this picture up real quick, where we have all these different pictures of receivers, all these different pictures of cornerbacks, and we're going to utilize that for the AI to be able to train off that data, right? So we have the pictures. So let's, as we always do, come here to our handy dandy AI assistant and try to figure out how do we start actually labeling the data. Okay. So simple. How do we start labeling the obviously once we're done labeling, then we could actually utilize those pictures, the data that we have. Oh, actually, if I remember correctly, the labeling works in regards to in regards to the pathing of the yes. So here we have our dataset image folder, which has data train. Depending on if this is, AI training cornerback, as we have here in this AI training area, we have our training data and we have our cornerbacks, which has all the pictures, and we have the receivers as well, which will contain all the receiver pictures, right? Now, with this being the case, um, it'll come to this training data and look at the CB pictures and understand that that is being labeled as cornerback, and the receiver pictures are understood to be labeled as receiver due to the parent directory's name. Okay. So let's come down here. And I remember now we were working with a supervised setup, which is what led us to asking what a supervised setup was. Because if I remember correctly, okay, not sure where it was, but let's go ahead and start with step one, right? Define exactly what one labeled sample is. Give me 1 second, actually. So one image that shows exactly one player. All right. So let's start with a receiver. Yeah. So we're gonna look at the receivers, and we are gonna start with receiver front one. All right. Nice and simple. Receiver front one gives us this, and within here, tensors will be made in order to construct a pattern out of what we're seeing here. And input, label, uh, data, train, wide receiver. So let's just copy this data, train, wide receiver setup. Actually, no. Let's keep what we have now so we're forced to kind of understand this in our own schema of AI training, trading data, cornerback, right? Um, the folder name is the label frameworks. Okay. And the first setup is a picture with both a receiver and cornerback and it acceptable as one training example. No, because it's going to be, unless it's cropped around, no, it doesn't. Because it's going to have two players on it, but be labeled cornerback or receiver. So how can it determine which is which, right? So the answer to that is going to be no. One image equals one label. Nice. Manually crop each player. Slow. Yep. So we're going to start option A. Um, no. 200 to 500 is insane. Okay. Okay. So here it's asking if you have an image showing a cornerback lined up directly over a receiver, if you crop only the cornerback, so the only point of reference, the only data available is the cornerback, where does it go? Well, not receiver because this would label it as receiver. So we go cornerback because labeling as cornerback. Okay. Correct. The crop shows a cornerback, so it goes in the cornerback folder. The wide receiver existence in the original frame is irrelevant once you crop them out. Alright, what you physically do to start labeling. Make the folder structure once. So you need the train. The val is something. Okay. Reserve some image for validation. Fit the 10th image instead of putting it on the train. Put it under val. So what is validation doing? Right. Again, always stop if you don't understand something. Break it down to the smallest bits. All right. So what? Ah, I remember actually. We can do this. I hope it doesn't do just. I hope it doesn't just say validation, like what validation means, because. All right. Yes, we know what validation is. Let's see this. For purpose of balancing the performance, it's common done in machine learning to ensure that the model is not overfitting and not generalize both new and unseen data. I see. I see. So, okay. So right now I have these one, two, three, four, five, six, seven pictures. So now what I would also like is to have a validation data folder. And this is Linux that we're going to be doing this on, so let's make it Linux friendly. By Linux friendly, what I'm doing is I'm dropping it down to lowercase, no spaces, so I don't have to worry about um, quoting out things. Mm, I can do this on the other side, but I don't feel like it, quite honestly. Okay, so now I need another picture that is not relevant to these pictures. So let's come over here to, let's come here. And it's quite interesting to me, if I'm being honest, the fact that there are so few pictures taken at the line of scrimmage. This is clearly a receiver. We're gonna save that image. Come here to, actually, no. Open, link a new tab. Why am I struggling here? Wide receiver trip is crazy. That's a nice catch. I know they're, here we are. Yeah. Go ahead, get this cropped. I like the shoes. And we are going to go ahead and save that into the AI engineering, validation data, receiver val. Or, so we're just saying receiver val 1 for this picture. Save that. And then let's find ourselves another one by any chance. This is a good cornerback picture, but he's in motion, so it's not really going to work as a. This is good right here. It's pretty much the same exact one as this though, so I'm not. Let's find something different. Uh, let's see. Relatively decent, stationary, but this is more of a safety stance. Uh, so I have to slide. I have to pass on that one. All right. That is a picture and a half. Wow. I think I already have this. I already have this. I don't think I have that, but if I remember correctly, it's because the feet weren't showing. This is really good for both sides. I don't believe I have this already. Uh, I do not. Cool. So we're gonna use one of these for validation on the receiver side, and then the other one will be for validation on the cornerback side. So same concept. We take this receiver val 2. Same concept. We take this. Don't like that cropping. Take this. call this CB Val 1. Yeah, this is it right here. This is what we've been looking for. This is exactly what we've been looking for. Just a bunch of these. If you're gonna give me more, I ain't gonna say no. That's for sure. Like, if you're gonna keep giving me training data, then I will happily take it. I hope it doesn't, but this might be good in order to have a chance to deal with some other background noise. I think that's gonna be necessary as well. So we're gonna call this training data. We'll just call it React 1. Right. And just get more generalized. Now that I understand truthfully, they're talking about I'm gonna need 200 to 500 images. Yeah, we're just gonna let's start now renaming all these so that it's a bit more it's a bit more user friendly for me in the future. Worst case, I can do like a for loop rec for x in 1 to 200. Do something on rec underscore x, right? Eight. Same concept for the cornerback. Right. Oh, I could just tab it, say it ain't so. Oh, that's nice. I did not know I could do that. Alright. I have 8 for receivers, so let's get one more cornerback. Oh, that's cold. We'll take it. Try to cut off the helmet on the backside. We will take it. Hopefully, like I said with the tensors, yes, this black might mold into here, but the overall shape and form, it should work, man. It should work. Let's get 10 receivers at the very least. This is, I don't know about the watermarks. It might be problematic. You know what? let's throw back a little bit, right? Let's get a little throwback in here. Same concept. Receiver, right? 10. You know what I don't like, and that's gonna happen. I've never been a fan of. Um, let's get rid of all this actually. And then what I'm gonna do is copy from my C drive users. Hello. Ah, I don't see users. Alexander. Documents. Learn with Alexander. And then we're saying, if I remember correctly, AI engineering. And then we want training data to be, we're going backer directory because I really want it back one. So we'll put the training data backer directory as well as the val data back directory so we can use that. And then we don't need this training data here anymore. So we can get rid of that. And now, as you can see, we have our train CB wide receiver with all the PNGs, receiver has all the PNGs. And he should have. Yeah, this is what I was saying. I don't like is that it goes 110. I understand it, but I've just never been a fan of that whatsoever. All right. I do need 3 more cornerback, and then we will be good to start writing some code, I believe. Finally. Very nice. Don't think I have it. states. Fire. Save CB9. And then this is unique. Very wide stance, very low. Um, Hopefully, this will give me something to work with, kind of unique. I really want to make sure I'm catching all the gotchas. Not gotchas in a sense, but I just want enough variety to where it's obvious that. It's such a. These are such great pictures. I don't. Alami, whatever their name is, whatever that website is, they take such great pictures. I just wish the watermark wasn't there. Which I understand, right? You gotta make sure you make your money. I'm over here yoinking everyone's picture, but I ain't trying to make money off it, that's for sure. All right. So that in itself, this one right here, this is gonna act as one of our validations. So come here, validate it for CB. CB. Oh, I already have the third. Cool. So now same concept. We're actually gonna go ahead and delete anything, right, with data at the end. So let's get rid of the train data and val data, to which I can then come back here and just recopy it, make it easy for us. Now I don't want to go back a directory. I can just stay in this current directory. And we need train data as well. Now we have train data. 10 pictures. I know the receiver data has 10 pictures. I like the 10th one, val data. I think CB has three, wide receiver has two, which is fine. Yeah, that's whatever. Okay. So we have pictures. We have the directory set up. Now what do we do? Actually, let's do this as well. Right. We gotta source the bin activate. So now we're inside of our actual virtual environment with all of the we're inside of our actual virtual environment with all of the prerequisites installed. So always always make sure you got this going on. If that is what you're using, if you are just installing it all locally onto your computer, then I mean, hey, by all means, right? So what's next? So we have this. We have this. That's it. You're now doing supervised learning. Cool. Yep. I don't. Okay. This is a great question. So let's take a second and think about this, right? If I have 500 receiver crops, 80 cornerback crops, what is the most likely failure mode? Now, bias towards predicting receivers would mean because there's more receivers, it's gonna choose receiver more. And to me, that doesn't make sense. If anything, it may be the opposite because the amount of cornerback crops is lower, so its room for error is higher, right? Because it hasn't refined how it handles the process. But to me, I really think it's A. I could see C though, but let's go ahead. And I say A before I see the answer. I say A because at the end of the day, a cornerback is gonna look like an orange is gonna look like an orange. An apple's gonna look like an apple, right? Just because I have 20 apples and only 10 oranges doesn't mean all of a sudden it's gonna see orange and think red, right? B. Okay. So I was completely wrong. Like I don't think you can be more wrong than the as wrong as I just was. I see. I see. It might learn literally just to guess receiver because it's right. I see. Okay. Input space. X equals image of one player. Y turns into a receiver or cornerback 0 to 1. Yep. And this is calculating the loss. So now that we understand the difference and why this would be bad, if it's predicting on every image with 86% accuracy. Okay, I see what you're saying now. It's not the fact that, okay, it's saying, I don't know why I was thinking more so you're going through 500 receiver photos and you're just checking if it can determine who what a receiver is, right? As far as, nah, that doesn't make sense. Hmm. Nah, no. This is right. So at the time, at test time, the model predicts wide receiver on every image and achieves 86% accuracy. Why does it achieve 80% accuracy? Because it's probably about 80% more wide receivers than cornerbacks inside of the model. So it turns into a garbage model masquerading as good simply because of the backbone of it. It learned data set frequency, right? This is important. So let's data set frequency learning based on. Okay. Yep. We did all that. This is why we did all this. Okay. How do we start writing? Because we could sit here and go over all and I think it's important, right? But we're at a point now to where we pretty much understand this, at least the fundamentals. So I think it's important now to jump over to how we use these fundamentals. So, one line at a time, all right? We have this set up, and now we're working on our dataset.py, and let's go ahead and create that kind of at the top level, right? Or should we say make directory source, and then code data training or training.py. Okay. So first we're gonna import Torch. And as you can see, it understands Torch because we imported the modules, or we installed the libraries with pip, and then we're saying from torch utils.data import data loader. Now remember, the data loader is what's going to take these groups and coagulate them, combine them into something usable for the AI training. All right. So import, I believe it was torch dot something utils.data. Or sorry, I believe it's gonna be from import. Yeah, from import data loader. Go. And then from torch vision, I'm sorry. I'm trying to like go one at a time, but it's kind of annoying. I don't want this here. From Torch Vision, import datasets and transform. So datasets. Ooh, I forgot. Datasets are the key value pairs. So you have your image of what the directory is, right? You have your CB1, and then that has the label of CB. It's like a dictionary kind of. Well, Just transforms. Yep. So transforming is going to take it from, let's say, 500 by 500, and say we want to go 250 by 250 with some blurring on the jerseys so it hides the number with X, Y, and Z, and then transform it to a tensor and do all these different mechanisms onto the actual image itself is where we go in order to actually be able to use all of them and trust the fact that we're using all of them in a coherent and cohesive way. So from Torch Vision, and Torch Vision being the library with the capability to actually parse video, right? Data sets and transform. I think it's transforms. It's transforms, yeah. Cool. So here we are. And next up, we're saying training directory, right? So training dir. Here's my thing about the training dir. So we're in source, so we have to go back in directory. And then we're saying we're in source. So we have to go back in directory into train data. Right? Because inside of train data, it has the labels for each folder. So train data is the training directory. And then the valdir for evaluating if it's correct or not on new images instead of being corrected on it. Validator. So we're creating variables for the hard-coded path of these, essentially the variable name, what we're looking for. So transform. So this is the transform variable. It's creating an object of the transforms class. Um, so we're gonna call this Bumblebee because I like Transformers, honestly. And we are going to be using the transforms, right, from Torch Vision. We're going to be using transforms dot compose. So we are composing a transforms compose object. Okay. Now, what is going to be inside of this transforms component? Well, we know for sure it's going to be there's going to be like a dot to tensor because we need to turn it into a tensor. We know there's going to be like a resize because we want them all to be the same size. We know maybe a blur, right? We know maybe a remove background, maybe, right? Nah, we might need that. Um, we know what else. Let's genuinely try to take a second and think about what else could we do with a picture, right? Orientation. Is it, horizontal? Does it need to be vertical? We can shrink. We can resize. We can blur. We can change the color, but we don't really want to do that, in my opinion. So let's see what it has for us to say. Resize, normalize. So what is this doing right here? Pretty simple, right? We're saying, okay, it's doing a normalize of mean and STD. So your standard, but what, right? What's the mean of what, right? Let's let's figure this out. And like I said before, I want to be really good with notes. So transform parameters. We're gonna do something like this. If I can, to tensor, and we're gonna go down each one. So normalize. Make this pretty. Normalize to tensor, resize, which is pretty obvious, right? Um, Two tensor resize, normalize. Okay. So those numbers are not football specific and not RGB magic. All right. So they are simply the mean and standard deviation of pixel intensities across the ImageNet dataset. All right. So standard deviation of pixel intensities across the ImageNet dataset. So what is the ImageNet? Actually, yeah, what is. But if I'm, hmm, I don't think I'm understanding. Right? If right, you have an understanding of like, okay, you're asking what ImageNet is doing here in a wide receiver cornerback classifier when football has nothing to do with cats, dogs. Okay, so yes, ImageNet is simply an image database, 14 million images, and it has to do with a bunch of nouns. Okay, answer is not about content; it's about visual features. Blunt version. When you load a pre-trained model, so what is a pre-trained model? My understanding of what a pre-trained model is going to be it's already done the difference between an apple and an orange, it's done the difference between a dog and a cat, between a car and a bus, between all these things, right? So it's a pre-trained model already can differentiate between objects by image. Yes, perfect. Perfect, perfect, perfect. But then that's the rub, right? Is is ImageNet trained on football positions? Exactly. Perfect. 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 I 100% understand. So we're using ImageNet for something, but not for the actual purpose of it, right? It's not for all the pre-trained stuff. We're not sitting here saying, okay, we're going to use ImageNet to determine between an apple and an orange. We're just borrowing the brain that has already learned to see. Extremely general visual filters. Okay, so these are convolution filters that we're going to use after the tensor is made. Generic vision building blocks. Okay. So what I'm going to say here, future, all right? Learn about ImageNet. No, 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 no. What do I want to learn? Learn about training filters personally. Because it seems like for this, we're going to be using the filters that ImageNet already has provided for us. But um, in the future, we want to be able to say we can handle the filters on our own and not even use ImageNet, right? Like I understand the purpose. I understand no need to no need to reinvent the wheel, but I also feel it's extremely important for me to oh perfect here. Early for the start random, don't detect hashes, nothing conversions, hundreds of thousands of labeled. Oh, okay, okay, that's fair. That still doesn't change. If it means I have to scrape build a web scraper for wide receiver, cornerback, crops, and build a program that supplies that for me so that I could train off hundreds and thousands of that, so be it, right? Oh, that's crazy. Okay, this is awesome. So ImageNet already has all these different filters. Wonderful. So, okay, that's wonderful. So, okay, okay. Performs functions on image to mirror standards of other tools if desired. My best way to explain that definition, right? This is perform. This word be killing me. I'm not even gonna lie to you. Okay, so normalizing, resizing, done. And then two tensor, done. It changes it to a tensor. Um, so from here, we are now in a position to where we can say, okay, let's go ahead and work on our transforms, right? So we have two tensor, we have the resize, and then we have the normalize. I think it's capital normalize. Okay. So let's look at this. We're resizing to the same height and width all across the board. Right? So 224 by 224 transforms, resize. We're using it inside of the compose. So we're saying transforms dot resize, and then it was 224, 224. I think it was quoted, if I'm not mistaken. Then doubled, double parentheses. Okay. So then we have our transforms dot two tensor. I think it's two tensor. And this should be a comma if I'm not mistaken. Uh, capital. And then lastly, we have our normalized. Is this double quoted as well? Or double parentheses? No, single. Single, break it open. And then transform. So the mean, alright, so the mean. So what, I understand what it's doing, I understand the process, but what is, what is these actually calculating, right? What is it actually checking? Uh, Mean and standard deviation in the ImageNet normalization of not checking anything, they're used to shift and scale the pixel value so every channel has a consistent statistical baseline that helps the network train. Okay? So, what I like about this right here, this moment, I understood every word that was used here, right? Normally, we say something, we get through the first paragraph or so, we don't really understand the word, we have to go off, check something else, but we understand everything that's going on here, but this is one of those moments where you don't really understand the context, though, right? So let's break it down. For each color channel, RGB, the ImageNet researchers calculated the average pixel intensity across the whole dataset. So, average pixel intensity is the average color across the entire dataset for red, green, and blue. Okay? And then for each color channel, it either goes up or down 0.229, 0.224, 0.225. Right? So basically, the intensity of red at 0.485 is the mean, and then it can go up or down by 0.229. Average normalized pixel value of the red channel. Well, that's what I'm saying, right? Square root of the average the square root of the average square deviation. Are they hard? Plus minus change. Okay. Yes, I understand that. And then this is something I need a little bit more digging for standard deviation. Standard deviation. How spread out a set of numbers is is a measure of how spread out a set of numbers is. Should it be is or are? I don't know. Low standard deviation, high standard deviation. Okay. So n is, I guess, the number of values, mean of the values. Okay. Takes values get shrunk because they're naturally spread out. And the standard deviation is small. The takes values get stretched, especially after on the raw difference. Okay. A tuition, perfectly uniform values, no standard deviation. Mean is zero point 0.5, nothing varies, zero standard deviation. So if you subtract the mean but do not divide by standard deviation, what happens to values on a channel that actually have a large variance? Okay, so let's first, I think we need to understand what pixel intensity actually is. I might be off on that. I might be off on that. How bright a specific color channel is. Brightness of red. Okay. Black, full bright. Okay. So one is full brightness. Black is no light. How many pixel intensity values exist in total? Well, 224 by 224 would get you all the pixels. But then you have to account for the fact that each pixel has an intensity of three different channels that it could be working with. Okay, the entire wide receiver versus cornerback classifier. What's a classifier? Classifier is a word or a favorite no. Data science for tasks such as image recognition, sound detection. Okay, classifier is just saying is it receiver or cornerback. The entire classifier starts from nothing more than three because you have each channel, height, width, numerical brightness values, no semantics anywhere. Everything the model learns beyond RGB intensity is driven by labels reducing loss. Nothing else influences learning. We are now ready to look at the actual evolution of tensors inside of a pre-trained model. We soon extract officer. Okay, so there's image number one with three RGB channels of 224, 224. Output shape. So you're saying image one, 64 channels. And then this is half. And then you're still lowering down while raising the channels. So why do the channels raise as we lower height and width? So as I'm noticing a pattern, as we lower the height and width, channels get higher, channels get higher, channels get higher, channels get higher. Um, so I would like to understand kind of where that's coming from, right? But so we're still saying image one with 512 channels, or is this layers? And then this is a 7 by 7 pixels square. Uh, what is it? Becomes a deep layer and alarm. And each stage needs to access a larger region. I see. What does provide a visual representation of each channel throughout steps? I'm not really understanding where, right? Three grids stacked. So stacked to me is, you have one grid filling this up, second grid filling this up, third grid filling this up, cut up into 224 by 224. Essentially, box, 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 little tiny boxes. Um, so instead of pixels, oh, are we saying we're making the image smaller or cutting it? So I'm trying to understand when we say 112 by 112, are we cutting the image in half, right? Are we saying cut this image in half and then only focus on this or this, or only focus in the area that's only catching something? or are we shrinking the entire image in order to stack more grids on top of it? Let's see here. Pop up paint real quick because there's a couple different ways we can go about it, right? You could say I have a grid, and this is 224. What the heck type of four is this? By 224. And this has its pixels, yada yada. And let's just say this is 224 by 224 pixels. Two. And that finishes. So then we take that full image and we shrink it down a bit into this. This is still the same exact full image, but now we're saying this is 112 by 112. And now this may have three layers, right? So this is red, the intensity of red here, the intensity of blue here, the intensity of green here, all found. So this though, on the other hand, is gonna have, one layer filling it up, finding something, then another layer, right? Then another layer, then another layer. And it's finding these patterns based off of the backing uh, ImageNet in order to find certain shapes, right? This is my understanding, but we're about to see. All right. You are assuming a manual resize has not happened inside the after because of stride and pool, not because stroke and artificial. First convolution layer typically uses a large kernel. Filter steps 2 pixels at a time instead of one. Oh, okay. So now you're looking at 2 pixels at a time instead of just one. So now the resolution is looking essentially at two instead of okay, okay. You're not cropping. You're just handling 2 pixels instead of one, so the resolution technically changes by half, right? Okay, I understand now. Reduces spatial resolution over depth, and then to save GPU memory. Wait, no. This is the real reason because we don't really care about this. We don't really care about that. B is the real reason the network reduces spatial resolution over depth so that it can handle deeper channels so that you can get larger visual patterns. If it stayed 224, well, see, but it's only doing this because the GPU has problems handling 64 channels of 224, right? It's either A or B. I'm thinking B because technically, on a technical level, this sounds more, concise and just better overall. And if we're thinking about axioms in the sense of like what's the invariant here, right? You don't necessarily need to save GPU memory for a bunch of GPUs, but this always is valid and always is relevant in the manner of what it's working with. So wonderful. See, I don't like this, right? I don't think I wonder if there's some type of back-end coding that tries to make you seem smarter than you actually are because there is no way. No, most people don't realize that this is getting quote unquote cropped because it's handling more pixels at a time. I don't know. More of the original image, not to make the image small, but to make patterns larger. Yep, 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 yep. Yep, yep, yep. Wonderful. Okay, awesome. And where were we? What was the point of that? Um, let's see here. So we understand pixel intensity now because that's just the color. Oh, we're still here. Let's see here. We checked on pixel intensity, and then classifier, show the model. Yep, nothing influence learner. So first convolution layer is 64 channels because we're kind of handling each pixel, 2 pixels at a time, looking for some patterns, still looking for patterns, and then here we're seeing the entire player. Wonderful. And then this, now the 512 layers creates the entire player. And then you go ahead and you make your decision based off of your confidence, yada yada. And then you add some loss to the training code wise. So let's see. Okay, we are running out of time. Um, so what I would like to do before we wrap up is finish this transforms block. We'll go into data sets and data loaders afterwards because again, I want to make sure we go deep into it and understand everything. So let's finish this block for transforms. So the mean is across the entire ImageNet system. What is the mean? Right? This is something I'm going to copy paste because I don't feel like flipping back and forth for decimal point. But key, right? This is key. This is so important. Don't just go around copy pasting everything, right? If it's decimals inside of the variable that you're creating that works with the normalize function inside of the transforms class, inside of the compose, whatever, right? Cool. Yeah, copy paste. But the whole overarching thing, work through it. Um, I think that's key. I think that'll take you way further than anything else. I sound like my mom growing up. She used to always tell me, write it down. Don't take notes on your computer. Don't take notes on your laptop. Write it down and you'll remember better. And this feels like the new age of that. All right. Write it down. Type it out. And then we have our normalize. Was not closed. Could mean it wasn't closed. It's right there. Was that somewhere else? There. Uh, normalize. Ah, I see. So we have our resize, which is going to resize to that size, which will then is why the normalization layer, uh, well, not normalization essentially, but when it starts training, it's going to go from 224 to 112 to uh, keep going down, down, lower, lower. Create the tensor for it to actually work with, normalize it based off of the ImageNet, and then that is it for now. Next up is data sets and data loaders, right? So we're gonna get a chance to really dive into data sets, data loaders, how they work, um, good loaders from bad loaders, maybe. I don't know, but we'll see. We'll get there. That'll be tomorrow, and I I feel good. I mean, we got some new images, set up our training, got our source code, and from here we should be able to finish up the data loader tomorrow and hopefully get some training running. So that is it for today. Let's see, get my day 7 ready with y'all real quick. Um, let's see, data. All right, wonderful. That's all I got for y'all.